Assalamu alaikum. Today we'll discuss Article 29.4, that is motion of charged particle in a uniform magnetic field from Survey and Joule. In this article, first you'll see that this equation, which is Lorentz force. We have gone through Lorentz force in Article 29.1, 2 as well as 3. So now we are quite familiar with this equation over here. So now suppose that we have a charged particle, that is plus q, and we release this charged particle at a certain angle uh, as shown in the figure, and the direction of the magnetic field is coming out of the plane, that is coming out of your laptop screen. And when we have velocity moving in this direction and the direction of the magnetic field is coming out of the plane, then the direction of force will be in this direction. So when these forces, this force, velocity and magnetic field, they act in the given direction, this charged particle will be changing its direction at every point and keeping its speed constant. So if the speed is constant but the direction is continuously changing, we say that this charged particle, it has certain velocity and is moving with some acceleration, because the velocity is changing its direction continuously. Therefore we will be having different signs for that. So now the particle is forced to move in circular direction and in circular path, and the radius of this path is given by capital R. So we have one force, that is when a charged particle is moving in a uniform magnetic field, we have this Lorentz force. And when the particle is moving in circular direction, then another force is acting on the charged particle, which is forcing this particle to move in circular direction, is FMA, and here this A is C. That is Newton's law, and this AC is for centripetal acceleration, which means that if we have this centripetal acceleration, then this force will be centripetal force. And we know that from our previous knowledge that centripetal force acts on a body to make it move in a circular path. So now we have two forces acting on this particle. One is the magnetic force, that is F is equal to QVB, and the other is the centripetal force, that is F is equal to MAC, where again from our previous knowledge of mechanics, we know that centripetal acceleration is equals to V square over R. So I can replace this AC with V square over R, and I get this centripetal force. Comparing these two forces, I get QVB equals to mv square over R, cancelling velocity from the both sides, and we can easily find the value of the radius of the circle if we know the mass of the particle, velocity of the particle, charge, and magnetic field. If we have electron, then we will use the mass of electron, and if we have proton, then we will use the mass of proton and any other particle which we are considering. For velocity, we must know the velocity with which the particle is moving, and the charge is that in coulombs, and the magnetic field, in this case we have uniform magnetic field, and we must know the value of that magnetic field. From here we can see that R is directly proportional to mass and velocity. If we have heavier particles, then the radius will be greater, and if the velocity of the particle is large, then we have a bigger radius as well. But in this case, if the magnetic field is stronger, then the radius will be small, and if the charge is greater, then the radius will be small. So these two are inversely proportional to the radius, and mass and velocity is directly proportional, are directly proportional to radius. So from here, if you look at this equation number 3 closely, you may see that this mv also reminds us something from mechanics, that is the linear momentum. So if you remember, we used to study linear momentum is equals to mass into velocity, and I can replace this mv with a p, that is linear momentum. So from here I can see that this radius is directly proportional to linear momentum as well. This is how we can easily find the radius of the circular path in which the charged particle is moving if it has certain velocity and magnetic field and the force acting on it. So from here we can also find the angular speed of the particle, and we know that angular speed is equals to v over r from this equation over here. All right, this equation over here, we can find v, that is v is equals to q b r divided by m. So I can use this equation to find angular momentum. So qbr over m divided by r is cancelled, and I get omega is equals to qb over m. So this is how you can easily find the angular momentum. Now if you want to find the time period of the motion, that is time to complete one revolution. So we know that time period is equals to 2 pi r divided by uh, v, and from here we can simply replace this v with omega r, and or we can replace this v over r with omega. So omega is equals to v over r, so I can write t equals to 2 pi over omega, and from here we can replace the value of omega and can find that time period is equals to 2 pi into mass divided by q and b. So from equation 5 and 6, we can see that omega and t, they do not depend on linear speed or radius of the orbit. Omega is often known as cyclotron frequency. So if a charged particle moves in a uniform magnetic field with its velocity at certain angle with respect to b, its path will be helix. So now if I have this charged particle and I release this charged particle at certain angle with this uniform magnetic field present over here, then this field will force this charged particle which I have released in this uniform magnetic field at certain angle to move in a helical path. So the charged particle will now move in a helical path. So whenever you release a charged particle at certain angle in a uniform magnetic field, and the path the particle will follow will be helical. So if it is moving in x direction, then there is no component of force in x direction. So we can say that ax is equals to 0, that is the velocity remains constant. So if the velocity along x-axis remains constant, then the change in the velocity will be in the y and the z direction. So we can find v equals to under the root vy square plus vz square. Uh, so from here we can use this equation to find the velocity. We will calculate the velocity for the helical path by using this equation, and again we use this value in this Lorentz force over here. So now coming to examples, example 29.6 is related to the article. So a proton is moving in a circular orbit of radius 14 centimeter in a uniform field of 0.35 Tesla to the velocity of the proton. Find linear speed of the proton. So we have to find v. Radius is given 14 centimeter, which is 14 into 10 power minus 2 meters. A magnetic field is given, mass of proton is known to us, and the charge on proton is also known to us. So we will use this formula, V equals to QBR over MP, putting in the values, and the speed, linear speed is 4.7 into 10 raised to the power 6 meters per second. In example 29.7, it says that in an experiment designed to measure the magnitude of a uniform magnetic field, electrons are accelerated from rest through a potential difference of 350 volts. So potential difference, that is V, delta V is given. The electron travels along a curved path because of the magnetic force exerted on them, and the radius of the path is measured to be 7.5 centimeters, that is 7.5 into 10 to the power minus 2 meters. If the magnetic field is perpendicular to the beam, we have to solve two parts. In A part, what is the magnitude of field, that is we have to find V, and in B part, what is the angular speed of the electrons, so we have to find V. Initial velocity is 0 and potential is 350, radius is 7.5 into 10 to the power minus 2 meters, charge is 1.6 into 10 to the power minus 19 coulombs. So to solve this, we again use our previous knowledge, that is conservation of energy, that change in kinetic energy plus change in potential energy is equals to 0. So here in this case, the potential energy is minus q del v. We have minus sign over here because we are talking about electrons. So kinetic energy is 1 by 2 mv square plus minus q delta v, that is for potential difference. So from here, rearranging the equation, and to find v, we have rearranged this equation, now putting in the values, and I get v equals to 1.11 into 10 raised to the power 7 meters per second. We have to find this magnetic field, and the magnetic field can be calculated by using this formula, that is mass into velocity divided by charge and radius. So putting in the values, and I can easily calculate this magnetic field over here, which is 8.4 into 10 raised to the power minus 4 Tesla. Now in the B part, we have to find the angular speed. We know that angular speed is equals to V over R. We know the value of V, we know the value of R. Simply putting in the values, and we get 1.5 into 10 raised to the power 8 radians per second. So this is how we can find the angular speed. So this is all about article number 29.4 and its related examples.